same one you did. And I was about to do pass the demo. Oh, okay.
I'm so bad at
It is slow.
Him and Dr. Mo, I'm always looking at every time, every time I sit there and try to listen to Dr. Mo.
You just read the book. That's
Yeah.
his lecture.
I like Dr. Mo's class. I feel like I'm the only one that like
I love no, I hate it.
I learned so much.
I don't. I learn absolutely nothing.
I guess I was only taking 14 hours as a semester, so I spent a lot of time.
I think it's 7 years.
That's rough.
It's my third semester back to college.
I did 14
I should have
last
used to it.
semester, and I thought I was Amy learned.
Dang, you have a lot.
Luckily, I only have one. Luckily, one work's done. So basically, done. Chris is doing all of them.
Okay, so good morning, everyone. Before we start, I just want to distribute this. And discuss it with everyone here. Okay, I want to discuss this with you, not just give it to you. Here, let me grab the assignment for this report and see what you were required to find, okay, or do. So, please take notes of why you lost points here, okay?
Are you taking this back up?
No.
Okay.
State pitch competition. Report. By the way, I uploaded report 4. This is a group report. I divided you into 2 groups, okay? So please work on that group report, okay? You're divided into 2 groups now. Let me open this. This is the individual design report and what you were required to find, okay? Or do. I just want to show you that you didn't adhere to what you were required to find. That's why most of you lost many points, okay? A lot of points here. So you were required, it was so detailed, you just didn't follow what you were required to do, okay? You were required to draw a fully detailed and dimensioned top, elevation, and side view. I wanted fully detailed and dimensioned. I needed to see dimensions, okay? In the 3 views to understand and make sure that your design adheres to the rules. If there were no dimensions that let me understand, okay, how the members are oriented together, The distances between the lengths of the members, the distances, every fully detailed, fully dimensioned. If you didn't have this, okay, so this is the points here. This part, okay, was 30 points, okay? So if you just gave the views without dimensions, you lost 15 points, okay? So that was the first thing, okay, that you were required to put, okay? 3D view of the bridge, that was 5 points, okay? Figures showing different member sections. So each member that you have in your design, if it repeats itself, then you just have to draw a details for that member, okay? When you're showing details for that member, I should understand how is that member built? What's the dimensions, okay? What are the sizes of the components building that element? Is it a hollow section? If it's a hollow section, so what's the thickness of the wall? I need to understand the details of each member, okay? That part was 15 points, okay? It has to be fully detailed, fully dimensioned as well, okay? Stead results for lateral deflection for different loading cases. Lateral deflection, okay, so for the lateral deflection, you have 2 lateral deflections, okay? Why 2 lateral deflections? If you see the 6 loading cases, you will see that the lateral deflection is measured at 2 points, okay? Just 2 points. So I need to see this in a table, okay? How much is the lateral deflection for the 2 points, the 2 different points where they are measured, okay? And then this part results for the aggregate deflection for different loading locations. What's the aggregate deflection? The aggregate deflection is the summation of the vertical deflection at point D1 and point D2. Where are point D1s and point D2? Just read your rules and you will know where's point D1 and point D2 for each case. So you have to report the deflection at point D1, you have to report the deflection for point D2, and sum them together, it gives you the aggregate deflection, okay? If you just plot the results that you get from the stead without putting this in a table, what's the deflection at point D1, what's the deflection at point D2, what's the aggregate deflection, the summation of them, for each of the 7 load cases. You have 7 different load cases. You have to show those results for each load case. That's what you were required to find here. Results for the aggregate deflection for different loading locations, okay? Not just tell me the maximum deflection is 0.6. The maximum deflection might not be at point D1. I want you to report the deflection at point D1, not the maximum deflection. You just plot from the stead that the maximum deflection is equal that value. No, I didn't ask you for the maximum deflection. I'm asking for the aggregate deflection, which is the summation of the deflection at point D1 and point D2. You should report the deflection at point D1 and point D2 for each case and sum them together, okay? So here, those 2 parts here, you have this deflection, two deflections at point D1 and point D2, okay? Plus the aggregate deflection, so that's 3 deflections that you have to report in each case, times 7, so that's 21 deflection. And for the lateral deflections, that's 2 deflections, okay, or 2 displacements, so that's 23. 23 deflections or displacements that you have to report, multiplied by 2 points each, that's 46 points. If you didn't plot or put that table, okay, the deflection at point D1, the deflection at point D2, the aggregate deflection for each of the 7 load cases, the lateral deflection for the 2 different, you have six load cases, but you have to, it's going to be just 2 points, okay? If you don't put those values, you lost 46 points, okay? The total weight of the bridge, if you didn't write the total weight of the bridge, that was 4 points, okay? If I don't see the total weight of the bridge, that's 4 points. And then you will require to find the structural cost, okay? Based on the equation that for all load cases, okay? that's 5 points. If you didn't find the construction or the structural cost, that's 5 points. Okay?
So the stringers, after they connected to the footing, you could have like the stringers connected to the beam that are connected to the footing.
The stringer is that, beam running from the start to the edge to the end of the pitch. And then you have the loading rail. The loading rail can be part of that stringer or not, whatever you want. Okay? The stringer has to be supported by the columns or the footings, definitely. They're not going to be just in the air. How they are supported.
Oh, I had it connected to the beam.
No. So what do you mean the beam? You just
The
have...
beam, like it's the cross member.
Okay, and what is supporting the cross members?
Footing.
Okay, but the cross members you just...
And I had the girders going across the outside.
Okay, we have to see this together, and I remember your design. We're going to discuss this. Just, we're going to discuss it. Don't worry about it. Okay? So that's for CS. I want you to find CS for each of the 7 load cases. And then the total number of connections. You have to count the total number of connections, okay, between different members, okay? That's 5 points. And then the construction cost, that's 5 points. The construction cost is so easy. That's just the number of connections multiplied by 20 seconds. And then the overall performance, which is CS plus CC, okay? That's 5 points. Those are 120 points, okay? So you can see where you lost points here, okay? And then your design has to adhere to the rules, right? If your design doesn't adhere to the rules, it's not going to be in the competition, right or not? If your deflection is more than the allowed range, and you should know what's the allowed range, right? Because that was the first report. You were required to know what are the allowed ranges for the deflections, for the distances, right? So I have here penalties, okay? For any dimension that is not compatible with the rules, I'm subtracting 25 points, okay? If your deflection is beyond the limits, okay, you're losing 40 points. Actually, you should get 0, because if your sway is more than 1 inch, according to the rules, okay, it's not going to be in the competition. It's just going to be eliminated. If any given vertical deflection is more than 2 inches, okay, 2 or 3 inches, if any vertical deflection is more than 3, it's more than 3 inches, your design is eliminated, okay? So you should get 0, because this design is not going to, it's not going to be, judged. It's just going to get eliminated, okay? So you should get 0. I'm not giving you 0, I'm just subtracting 40 points, okay? So that's why you lost those points, okay? You can just go through and understand why you lost those points, okay? The report here was so clear that you should put those things, okay? You just have to follow what you're required to report, okay? Yes, Dylan?
On that input dimensions on 3D members, the 3D structure, otherwise I have the dimensions. So that only counted off because I didn't do it on 3D.
If the dimensions are not enough for me to understand, the orientation of the members, how the distance between the members, okay, then I'm subtracting points, okay? Your dimensions, you're not giving dimensions just to fulfill that you're giving dimensions. The purpose of giving the dimensions is that I understand, okay, the size of the members, that I understand the distance between the members, and how they adhere to the rules. If I couldn't judge this from the dimensions that you're given, then you're losing points, okay? So now I guess most of you, you lost a lot of points, okay? So right now that you understand why you lost those points, okay, I will give you another chance to resubmit this report again. Just fix the problems that you have, because with the grades that you're getting for this report, this is not going to be good for for most of you, okay? So I'm giving you another chance to resubmit this, okay, and I will give you the average grade of this report and your resubmission, okay? So you're allowed to resubmit it again. You have until Friday of next week, the end of next week, okay? So you have a chance to still work on this, fix it, okay, and resubmit it. Yes?
I guess your questions I can ask at different time in your office, because I have questions about how to show some of that stuff. I didn't figure out on Friday. I'll just ask you this.
Okay. I have my office hours. My door is always open, okay? If there is anything that you don't know how to do, you just contact me, okay, during my office hours or anytime my door is open. Just contact me and I'm willing to help, okay? Some of you, they come, I can sit with you, I just go to the computer lab with you, okay, and help you with your design. I have no problem with that, but you have to ask for help. If you have a problem, something that you don't know how to do, okay, you're confused about something, the results are not, not getting good results, just ask me, okay? I'm here to help you, but you have to ask for help. I'm not going to go after each student. Do you need help? Do you need help? Do you need help? You have to ask for help, okay? Okay, so you still have another chance, okay? But you're not going to get full credit in the second chance, okay? So you work on this and make it better, okay? With the grades most of you are getting, it doesn't seem for me that, you're going to get a good grade, okay? That design was very, very important, that individual design, that's the major part, okay, of the design process, okay? Each student has his own individual design. It has to be correct, adhering to the rules. The deflection should be within the range. And then the fourth report, the report that we have after this one, is trying to optimize that design. So how would you optimize the design if your design is not working in the first place, okay? So you have to have a working design so that you can optimize that, okay? So for some of you, I'm giving you a hint on how to optimize. So some of you, like, their design are good, it's within the rules, okay? But let's say it's too heavy. So that's your optimization now. You try to make it lighter, okay? With, definitely if you're going to make it lighter, the deflections are going to increase, and that's what you want to see. If you make it lighter, okay? Yes, the deflection is going to increase, but what about the overall performance? Will it increase or decrease, okay? So it's an optimization problem. You don't know how it's going to work, okay? So you want to try different designs, okay? Maybe just, like optimization here is maybe an easier way of doing optimization so that you don't change your design. Just change the dimension of the members. So let's say you're assuming a wall thickness of 1/8 of an inch. You want to make your structure lighter. So instead of 1/8 of an inch, I'm going to make it 1/16 of an inch, okay? And see how much, saving in terms of the weight of the structure I'm doing and how much the deflection increased. And by doing that changing from a wall thickness from 1/8 to 1/16, did the overall performance get better or get worse, okay? Okay, so you have to try doing those optimization. But first, your design has to be good, okay? Any question? Yes?
You were talking a second ago about 40 points off, deflection is above so-and-so, and you're going to be subtracted. Does that apply to the resubmission of this or the fourth report, final report?
The resubmission of this, okay? Some of you are not even reporting the deflection, so I'm not able to judge if the deflection is within the range or not, okay? You're not reporting the deflection. So how can I judge that? Okay? The deflections here are they are 46. There are 46 points for reporting the deflections. I need to see those deflections. Okay? And then please meet together. I have the last one here. This is the last report here. So I'm dividing you into two groups. So this is group one. So please, for those students, please meet together, okay, and see each other's design and try to make sure that those designs are correct. Work together to fix each other's designs, okay, and start, working on those designs, trying to optimize those designs, those 5 designs to reach one perfect design, and then work on that one perfect design, okay, that you see that it's the best out of those 5 designs, and work on it to optimize it so that it has the minimum cost, okay, the minimum overall cost. So this is, again, please adhere to what you're required to find and what the final report should include, okay? And those 2 groups will give presentations on the last day of class on November 29th, okay? So please be prepared to give their final presentation, just 2 group presentations on November 29th, okay? Any question? So if you didn't submit your individual design, you still have a chance to resubmit it. You're going to get 50% of the credit, okay? That's Friday of next week. So everyone has the chance of resubmitting that individual report by Friday of next week, okay? But you're just going to get the average of the 2 grades, okay? So this is not here. Okay. Let's see this. What else did I want to discuss with you? Yes, for the midterm exam, I'm so sorry. I just forgot what time did you want to have it? Tuesday or Thursday?
Will we get our homework back that we're doing before the test since it's open?
The homework is due Thursday.
Isn't that what we're being tested over?
Yeah, beams are going to be included on the test.
Stiffness.
Yeah, using the stiffness method. So on the test, you're going to have frames using the slope deflection method, and you're going to have beams using the stiffness or metric structure analysis. Okay? So that homework is going to be part of the test. If you're going to submit it on Thursday, I can get it back to you by Monday, but the thing is, I'm not going to be in town to give it back to you. So I don't know how to give it back to you.
You do post the solutions after we turn it in on Thursday.
Okay. We can definitely do this. But just remind me, when did you want to have the test? Tuesday or Thursday?
Tuesday.
Yes. We actually have it scheduled on Thursday. What time do you want to have it? You told me last time, but I just forgot.
Yeah, because I changed my mind from last week.
Are we deciding on next week between Tuesday and Thursday?
Yeah,
Yes.
Tuesday or Thursday of next week. We have it scheduled on Thursday. So do you want to have it on Thursday? Who wants to have it on Thursday?
I don't really care. Yeah, it doesn't.
I'm going to decide.
You're neutral?
Pretty much.
Okay. If you're neutral, just don't raise your hands. Okay? Again, Thursday, 5. Tuesday, just 1. Okay. So it's Thursday. So we didn't change the midterm exam. It's what's on the syllabus. It's on Thursday. Okay? We didn't change that. It's Thursday. Okay? Of next week. That's about the midterm exam.
Tuesdays is open.
Hmm?
Tuesdays is open note test.
Tuesdays what?
Is it open note test?
No, I didn't say it's a,
Okay.
no. Okay. So on the test, you're going to be given the slope deflection equations. You're going to be given the stiffness matrix for a beam element, and that's it. Definitely the table for the fixed end moments at the back of your book. Okay, that's the only things that you're going to be given on the test. It's not an open note test. Okay, you're just going to have those at the last page of the exam. Okay.
Can I make a request?
Hmm?
Give us extra paper this time. I ran out of paper.
Yeah, I can do that. No problem.
I write big.
How many problems is it going to be?
2 or 3. Yes. That was your question? Okay. Once I decide, I will let you know. I'll send you an email. Okay? Okay. So last time we started solving that problem for the truss, solving the truss using the stiffness method. Okay? So we had that truss. What we did is follow the steps. The first step is the notation. I have 6 members, 1, 2, 3, 4, 5, 6, and 4 nodes, 1, 2, 3, 4, and 8 degrees of freedom. Okay? A vertical and a horizontal degree of freedom at each node. Okay? Those are the degrees of freedom. Some of them are unknown and some are known. I started labeling the unknown degrees of freedom. So the unknown degrees of freedom are the horizontal and the vertical degree of freedom here. So that's 1 and 2. The horizontal and the vertical degree of freedom here, 3 and 4. The vertical degree of freedom here, the vertical displacement here, that's the 5th. So those are the unknown degrees of freedom. And then the known degrees of freedom are the 6, 7, 8. Those are 0 because of the supports. Those movements are zeros. So those are known. And then the second step is building each member stiffness matrix in the global direction. Okay? So K, the stiffness matrix of the element in the global direction, is EA divided by L multiplied by this coefficient C and S. What is C and what's S? C is cosine the angle theta between the global x-axis and the local x-axis, okay, of that member. So the direction of the member is very important. So here you have to know and understand that the start and the end of the member plays a very important role, okay? If you switch the start and the end, the direction is going to be switched, being instead, let's say, instead of being positive 45, it's going to be negative 45. So that since you have an angle here, the direction, how you label your member, the start and the end of a member, is very important. So here we started doing this for member 1. Member 1 here starts at this node and ends at that node. So the direction here, this is the direction from the start to the end, okay? So theta is 0 from the global, that's the global direction, and that's the local direction as well. So theta is 0, so C is 1, and S is 0. Cosine 0 is 1, and sine 0 is 0. So definitely here, those are going to be zeros, okay? Those are going to be zeros, those are going to be zeros, those are going to be zeros, because they all have a sine term in them. Only the cosine is going to have a value, so you just have 1, negative 1, negative 1, and 1, and EA divided by L here. That's K for member 1, the stiffness matrix for member 1. So now for K for member 1, I just need to label it now. How would you label that? K for member 1. You label the degrees of freedom. What does the K, those elements in the K matrix represent? It's the stiffness coefficients relating the displacements to the forces at the nodes of the member, right? So what are the degrees of freedom related here? You have the horizontal, then the vertical, horizontal, then the vertical. The horizontal and the vertical at the start or the near end, the horizontal and the vertical displacement at the end or the far end of the member. So you have 1, 2, 6, 5. Okay? So that's the labeling of K1. So here we have 1, 2, 6, 5. And then K4 has the same value, so let me write K4 here. Let me just move this. K4 is going to be the same because K4 has the same direction, the same length, okay? But the labeling is going to be different. So that's K4. So just as a reminder, what's K4? K4 is the stiffness matrix for element 4 or for member 4. Member 4 here has the same length as member 1. It has the same direction as member 1. It has the same EA as member 1. So they look identical. The only difference is what are the degrees of freedom at the ends of member 4. What are those in order? It's the horizontal, then the vertical displacement at the near end, the horizontal and the vertical displacement at the far end. So you have 3, 4, 7, and 8. So for K4, it looks the same, but it's 3, 4, 7, and 8. 3, 4, 7, and 8. And then we worked on member 2. For member 2 over here, that's member 2, that's the start, that's the end. Who decide where's the start and where's the end? You decide, okay? If you want to say that this is the start and that's the end, that's fine, okay? It's not wrong. Any point, okay, can be the start and any point can be the end, okay? But once you say this is the start and that's the end, okay, it will affect the angle theta of the member, and it will affect the way you label your matrix, your stiffness matrix, okay, your element stiffness matrix. So here I said this is the first, the start, and that's the end. So the length of the member is 10 square root 2, square root 10 squared plus 10 squared, so it's 10 square root 2. EA is constant, and then how much is theta? That's the local x direction from the start to the end. That's the local x direction. Theta is measured from the global x direction to the local x direction. So how much is that? 45 degrees. Is it positive 45 or negative 45? Counterclockwise is positive. So it's positive 45 degrees. So for that member 2, L is 10 square root 2, theta is 45 degrees, and since theta is 45 degrees, so cosine theta is 1 divided by square root 2, and sine theta is 1 divided by square root 2. Substituting the numbers here, okay, you have c square, cs, cs, s square, and so on, okay? You have EA divided by L, so I actually divided all the elements here by L, by that length, okay? Now you just need to label this matrix, K2. How to label that? The horizontal and the vertical displacement at the start, and then the horizontal and the vertical displacement at the end. Where's the start? that point. So 1, then 2, and then 7, 8. 1, 2, 7, 8. One, 2, 7, 8. And then let's move forward. Is member 2 similar to any other member? Is there any member here that is identical to member 2? No. Why not? Yes, they have the same length, but they have different direction, different orientation. Theta for member 2 is 45 degrees. For member 5, theta is negative 45 degrees. So they are not the same, okay? The stiffness matrix is going to look different, okay? So let's go ahead to member 3. Member 3 is identical to member 6, okay? So once you build member 3, just copy it to member 6. Let's see here. Member 3, how much is the length of member 3? It's 10 feet, okay? What's the angle? To identify the angle of member 3, theta, the direction of member 3, you need to assign what's the start of the member and what's the end of the member. What I chose here, that this member 3 starts from point C and ends at point B. So that's the direction. So now theta is measured from the global x to the local x. So it's 90 degrees, okay? So for member 3, L still 10 feet, theta is 90 degrees, okay? So if theta is 90 degrees, how much is C? 0. And how much is S? 1, okay? So putting this into the stiffness matrix, you have EA, and then I'm going to divide each element by 10, okay? So here I have cosine square, so cosine square is 0. CS is 0. CS 0. S square, so it's 1 squared, so it's 1 divided by L, which is 10, so 0.1. And then the same here, but it's negative. And the same here, but it's negative, and the same here with a positive sign. So that's K3. Okay? Let's label this K3. It's the horizontal and the vertical displacement at the near end, and then the horizontal and the vertical displacement at the far end. Where's the horizontal and vertical displacement at the near end? 1 and 2. Why not 2 and 1? Someone would say, yeah, it's 2. 2 is in the direction of the member. I didn't say the direction of the member. I'm talking here about the global directions. The global x and then the global y. So x and y. 1, and then 2, and then 3 and 4 at the far end. Okay? So 1, 2, and 3 and 4. And then member 4, we already did member 4. That's the stiffness matrix of member 4. Let's do member 6 because it's identical to member 3. K6 is the same as member 3. Why? Because they both have the same direction and both have the same length and EA. And here you have to be smart, okay, when labeling those elements. You can definitely say that this member, this is the start and this is the end, okay? If you do this, try to have this member in the same direction. This is the start and that's the end. If you say, no, this is the start and that's the end, yes, you're free to do that, but their stiffness matrix is going to be different, okay? Because they're going to have different direction. So to try to eliminate, some of the work, try to have them in the same direction to have the same stiffness matrix for member 3 and member 6. So now for member 6, it's going to look the same. So I'm just going to copy this one here. And now we need to label it. This labeling 1, 2, 3, 4 was for member 3. Now we need to label it for member 6, K6 now. So let's see, member 6, what's the start and what's the end? How should we label member 6? The degrees of freedom for member 6. 6, 5, 7, 8. Okay? The horizontal and the vertical displacement at the near end, and then the horizontal and the vertical displacement at the far end. 6, 5, 7, 8. 6, 5, 7, 8. 6, 5, 7, 8. And then the only thing left is K5. How much is the length of member 5? It's 10 square root 2 feet. It's inclined member. Let's see here, member 5. That's member 5. According to what we assumed, that this is the start and that's the end. That's the labeling that we chose. So the length is 10 square root 2. And how much is theta? It's from the horizontal, the global x-axis, to the local x-axis. So it's negative 45 degrees. Okay? So the angle here is negative 45. So theta is negative 45 degrees. If theta is negative 45 degrees, so how much is cosine theta and how much is sine theta? In magnitude, both are 1 divided by square root 2, but the sine, cosine negative 45. It's positive, 1 divided by square root 2, and how much is sine negative 45? Negative 1 divided by square root 2. Okay? So as you see here, member 5 is not identical to member, what member was it? It was member 2. Right? Yeah. So let's build the stiffness matrix now. It's going to look somehow close to K2 because the cosine and the sine are the same in terms of the magnitude, but the sign is different. So I'm just copying this, and then I'm putting this here. Those are going to be different, and definitely the signs. The numbers are the same, but the signs are going to be different. What you're going to have here, you're just going to delete the signs and put the correct signs now. This one is going to be negative, 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 negative. I have something wrong here. 4 and 5, 4 and 5, that's negative. That's negative, negative. Let's see this term over here. That's negative. That's cosine square, right? Negative cosine square. So that's negative, yes. So that is negative. Sorry. No, the last one is negative CS, so that's going to be positive. Okay. So negative, negative. Okay, that's correct. So those are the signs now. Okay. As you see, in terms of the numbers, they are the same as K2, but the signs are different. Okay, because the difference here, this was negative. Okay. And now we just need to label K5. How would you label K5? Hmm. 3, 4, 6, 5. The horizontal and the vertical displacement at the start, and then the horizontal and the vertical displacement at the end. That's the start. And that's the end. That's the direction of the member. That's what we chose. So 3, 4, 6, 5. So 3, 4, 6, 5. 3, 4, 6, 5. Okay? What's the next step? The overall stiffness matrix. Build the overall stiffness matrix. So how big the overall stiffness matrix is going to be? 8 by 8. Okay? Each term I have EA as a common factor. 1, 2, 3, 4, 5, 6, 7, 8. So that's K. It's going to be that large. Okay? It's 8 by 8. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. You build those numbers. These are the numbers that you're going to get. 0.135. How to get those numbers? Mapping the elements from each member stiffness matrix. So 1 and 1, for example. Is there 1 and 1 in K5? No. Is there 1 and 1 in K6? No. Is there 1 and 1 in K3? Yes, but it's 0. Okay. Is there 1 and 1 here? Yes, 0.035. Okay. Is there 1 and 1 here? No. Is there 1 and 1 here? Yes. It's 1. So 1.035. So that's what we have. This is, by the way, this was divided by 10, so that's not 1. This is 0.1. So 0.1 and 0.035, okay, that we had here, that element. Okay? So it's 0.135. Okay? And you do this for all the elements. You just map them, okay? 1 and 2, member by element by element. So that's what you're going to get. 0.035, 0, 0, 0, negative 0.1, negative 0.035, negative 0.035, okay? And that's going to be the identical to the first column. And then the second row. It's identical to the second column. The third row. identical to the third column. The fourth row identical to the fourth column. And then the fifth column is identical to the fifth row. Then the sixth column row is like this, and then the seventh is and that's the eighth column. Did you need to build all and find all those numbers on the test? Will you do though so? You would do so if I asked you to write the overall stiffness matrix, but if I just ask you to solve for the reactions or the deflections or whatever, you don't need to find all of those, okay? So which part would you really need to calculate? You have to subdivide this into what?
Knowns and unknowns.
Okay, which is how much? How many unknowns did you have?
5 is none.
The first 5 are unknowns, so you come here. So 5 and 5. So which part did you really need to find? That part 5 by 5, what else? If you're only required to find the displacements, then that part 5 by 5 will be enough to find the displacements. If you need the reactions, you need this part here, which is identical to this part. So the only part that you actually wasted your time finding is this part. Okay? This part was not needed. If you don't have time on the test, please don't waste your time finding that part. When would you need to find some elements of that part of the matrix?
There's 7.
Yes, if there is movement of supports, then you need to find some numbers here. Okay? So that's step 4. Step 3, sorry. What's step 4? The load and the displacement vector. P is U is easy, okay? U is just how long or how big U is going to be. It's 8 by 1. The first 5 are unknown, which are U, X, C, U, Y, C, U, X, D, U, Y, D, U, Y, A, and then the rest are zeros. So this part is unknown, the first 5 are unknown, and then the rest, or the second 3 are known. They are zeros. Those are the displacements, okay? At the nodes, at the 8 or the 4 nodes, okay? The 8 degrees of freedom, 3, 4, 5, 6, 7, 8. What about P? The load vector is going to be 8 by 1 as well. 1, 2, 3, 4, 5, 6, 7, 8. This part, the top part, is going to be known forces, and the lower part is going to be unknown forces. Right? They are opposite of each other. You know this part, you don't know this part, so you know this part. You know this part, so you don't know this part. They are the opposite. Okay? So P, what are the loads at those degrees of freedom? 1, 2, 3, 4, 5. What are the loads at those degrees of freedom? Let's see the problem. What is the load at the first degree of freedom? The first degree of freedom is the horizontal here, at point C. Was there any load here? So it's 0. And then 2 was the vertical degree of freedom here, at point C. Is there a load there? No, it's 0. And then 3 and 4 are the horizontal and the vertical point B. Are there loads there? Yes. 2 and 4. Are they positive 2, negative 2, positive 4, negative 4? What are the signs of those two forces? Positive 2 and negative 4. So 0, 0, positive 2, negative 4. Okay? And then the fifth degree of freedom. The fifth degree of freedom is the vertical one here. Is there a vertical force here? No. So we have 0, 0, 2, negative 4, 0. Okay? And then the last three, 6, 7, and 8. 6 represents what? The force here, the horizontal degree of freedom. What does this represent? The reaction, the horizontal reaction of that support, AX. How much is this? I don't know. The 7th, it's what? BX. The 8th, that's BY. Okay? Those are unknown reactions. So let's write the load vector. So now the load vector looks like this. So we said that's 0, 0, 2k, negative 4k, 0. And then those are unknown, AX, BX, and BY. Okay? And then write the overall stiffness equation. That P, which is 8 by 1, is equal to that K, which is 8 by 8, multiplied by U, which is 8 by 1. Okay? So that's a set of 8 equations. How to solve this? First, you solve the first 5 equations. Just P, which is known, the first 5 are known, equal to this 5 by 5 multiplied by the 5 displacements. You just use your calculator to solve this, okay? So you solve the first 5 equations. The first 5 equations here. So solving the first 5 equations, you will be able to find the displacements. So UXC, UYC, UXD, UYD, UYA is equal to 1 divided by EA multiplied by 17.94, negative 69.2, negative 206, negative 87.14, negative 22.06. So those are the displacements at the nodes. Okay? Just solving the first 5 equations of that stiffness matrix. Okay? P, which was known, equal to this, multiplied by those unknown 5 displacements. Finding the inverse of that matrix and multiplying it by P, you're just going to get U. Okay? And then you can solve the last 3 equations to find the reactions. You have AY, BX, BY. They're going to be equal to negative 4K, 2K, 4K. Those are the reactions. Okay? Any question? By the way, over here, solving those equations, I just assume that you understand how you do this. If any one of you has a problem with solving those equations, he doesn't understand how to solve them, okay? Please stop by my office. Yes?
Stop by. Because I get the first part, the 5 by 5. It's the next one. It's the last equations that I.
Okay, let's do it now. So you understand the first part, but this second part is what you don't get. Okay, so let me write this here. What you have is this. Your stiffness equation says that P, so let's copy this. That's P, right? It's equal to K, right? So let me copy this, K. Okay? That's K, right? P equals K U, right? How much is U? You already understand the first part, right? So you know that those are the values of U, right? So 1 divided by EA. So you have here 1 divided by EA multiplied by those values, 17.94, negative 69.2, negative 206, negative 87.14, negative 22.06, and then 0, 0, 0. That's U, right? It's not unknown now. It doesn't have any unknown value. You already solved the first 5 equations, and you have the unknown figured out, right? Now, you have those equations, or those matrix. What's the multiplication of a matrix? The multiplication, you multiply the row by the column, right? So how much is AX? You multiply this row by that column.
That entire column top.
Yeah.
Okay.
So AX is what? Here you have EA, and here you have 1 divided by EA. They cancel, right? And then you have the first value here, negative 0.1 multiplied by 17.94. So negative 0.1 multiplied by 17.94. And then the second, 0 times negative 69.2. And then negative 0.035 times negative 2.06. And then 0.035 times negative 87.14. Right? And then negative 0.035 times negative 22.06. And then this one multiplied by 0, 0 multiplied by 0. I don't need to write them because they are multiplied by zeros. Right? So that's AX. You do this multiplication, you get negative 4K. Okay? And then you do the same. BX is going to be those values multiplied by the column. Okay? Any question? Does anyone? So now we explain how to substitute in the last equations to find the unknown reactions. Does anyone still have a problem with this, finding or solving the first part to find the reactions? To find the unknown displacements? Okay, so that's good. Now, is that what you were required to find? Let's see here. You're required to find the reaction forces and the nodal displacement. Did we find those? Yes, we find the reaction forces and the nodal displacement, the displacement at all of the nodes, okay? And also you're required to find the force in member BC. So how do you find the force in member BC, okay? That's tricky. You cannot, in this problem, especially, you cannot just use simple equilibrium. You're not going to be able to do that because this is an indeterminate truss. So equilibrium is not going to be, and this truss is internally indeterminate. So you're not going to be able to find the forces in member CB or any member just using equilibrium. So how would you find the force in the member? So now, member CB, let's explain this. There is an internal force applied on member BC. Okay? What's this? Member BC looks like this. That was the orientation of member BC, right? It starts at node what? What was the labeling? Member BC. It starts at node 1, ends at node 3. That's B. That's C. We labeled this 1. We labeled this 2. Okay? The force in the member is an axial force, right? It can be like this or like this. Right? That's a truss member. It can only have a normal force. There is no shear, there is no moment, right? The normal force is in the direction of the member, either tensile force or compression force, okay? So let's say any of those, okay? Let's say that the force here is in that direction. Okay? Definitely this is in equilibrium. So if this was member 2, we labeled that member 2, right? So those are the forces in the member, F2, F2. It can be compression like this or tension. If you're looking to find that force is in what direction? Is it in the local direction or the global direction? Local. It's oriented with the local x-axis. Okay? So to find this, okay, you need to turn back to the stiffness equation, but in the local direction. Okay? What does it say? So F2 here, F2 is the internal force in the member. And it is in the local x direction of the member. Therefore, once I ask you to find an internal force in the member, you have to revert back to the local stiffness equation. So therefore, use the local stiffness equation. What does the local stiffness, any stiffness equation looks like what? P equals KU. Okay? That's P. That's the stiffness equation. But now I have it in the local direction. P is small, K small, okay? And then U small. P equals KU. Let's see this here. P equals KU. That's what we had here. P equals KU. That was the local stiffness equation. P, which has two values, the force in the local direction at the near end, and F, the force at the far end, equals EA divided by L, 1 minus 1 minus 1, 1, U and X, U F X, the local displacement vectors. The local displacements of that member, okay? That's just for a member, okay? So P equals KU. So let's write this here for that element. That's the X direction, and that's the Y. So P, you have F2 is oriented with the positive X direction, right? So here you have F2, and the force at the far end is in the negative. If this is in the positive, this is in the negative, okay? So negative F2 equals K, which is EA divided by L. How much is the length of that member? 10 square root 2 feet. And then you have what? 1, negative 1, negative 1, 1. That's the local stiffness matrix for an element. Multiplied by the local displacements. What are the local displacements? U, X at the near end, and U, X at the far end. Do you know how much are those displacements? The displacement at that node in the local direction, and the displacement at that node at the local direction, not the global direction, not the global X and the global Y. Did we calculate this? No. What did we calculate? What deflections or displacement did we calculate? We calculated all the displacements, but in the global direction, right? We did calculate the deflections at every node in the global direction. I don't need the deflections in the global direction. I need the deflections in the local direction. Is there a relationship between the deflections or the displacements in the local direction and the global direction? The transformation matrix, right? Let's move back here during our derivation. We said U in the local direction, 2 by 1, U at the end, U at the far end, the near end at the far end, equals to the transformation matrix multiplied by U global. Okay? So just use this one. So the displacements here, let's draw the global displacements. That's X and Y. Let's label those. What labeling was those? That's the member. Member 2. Do you know how much is that displacement and that displacement? They are 1 and 2. The displacements at 1 and 2. The first and the second degree of freedom. How much were those? Those were 1 and 2, and those were 7 and 8. That one in the one was 17.94 divided by EA, and 2 was negative 69.2 divided by EA. 7 and 8. How much were 7 and 8? The displacement. 0. Because you had a support here, right? Point B, you had a bent support, so they were 0. So now, to find this local U local is equal to the transformation matrix multiplied by U global. U local, which is two values, which is U at the near end and U at the far end, is equal to the transformation matrix. How does the transformation matrix look like? You don't have to memorize it. I will give it to you on the test. Multiplied by the global displacements. What are the global displacements? 17.94 divided by EA, negative 69.2 divided by EA, and 0 and 0. Those were at those degree of freedom. 1, 2, 7, and 8. How much is cosine and sine? Cosine was 1 divided by square root 2, and sine was 1 divided by square root 2. So now you can just substitute that here. So therefore, F2 is equal to that part. I'll just remove that part now and put 1 divided by square root 2, 1 divided by square root 2, 0, 0, 0, 0, 1 divided by square root 2, 1 divided by square root 2, and then 17.94 divided by EA, negative 69.2 divided by EA, 0, 0. And from that, you're going to get F2 and negative F2. They're going to be equal to negative 2.56 and 256. So actually now I know the member like this. The force at the start is negative, so it's in that direction, 2.56 K, and this one is positive, so it's in that direction, 256 K. So what type of force is it? Is it a tensile force or a compression force? So that's a tensile force. Okay? So that's how you find the force in each member. You just need to use the local stiffness matrix, and you need to find the local displacements from the global displacements using U small equals to T, the transformation matrix, multiplied by U capital. Any question? Okay. Thank you.
Do you care if I get Brooke's report for her? Or does she need to come get it?
We're done at what? 4 hours.
She needs to come and pick it up.
Okay, I'll let her know.
Yeah.
You did not give me a group. I know
Yeah,
I
'cause
didn't turn.
Yeah.
Okay, I wasn't sure if that was why.
So, what was your design? Truss. You had a truss, right?
Yes, I was having a lot of trouble with it in SCAD.
Okay. So just work on that. You have until next Friday. Okay. And if you have a problem, just ask me. Okay.
Okay.
Unfortunately, I'm not going to be here next week. Okay.
Right.
But you have until Friday.
This week.
Okay. This week. Okay.
Okay.
So just work on it if you have any problem, and please adhere to the report. What are you required to
And I
report?
had most of it done. It's just my deflection. I couldn't get it to give me the weight, and it was really.
Just
Yeah, I'll come.
Yeah.
I'll come see you later.
okay. So since you have a trust, so just work with group 2.
Okay.
Okay.
Thank you.
You had a quick question.
So instead of having these numbers that I have that go all the way longitudinal,
Yeah.
do I need? Could I just like place the loading rail on top of that
So
instead?
you have those are the loading rails, right? And you have you have one. What do you have here?
Those are just extra longitudinal.
What's the section? Okay, you have to show that. Okay, that's one thing. Okay, so the thing is,